Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey everyone, just a quick announcement before we get you over to today's show. I'd like to invite you to join me on Thursday, August 27th for my conversation with Dylan Erb, co-founder and CEO of Paperspace, as we discuss machine learning as a software engineering discipline. We've been having a ton of fun with these watch parties, and of course, Dylan and I will be in the chat answering all of your questions about the relationship and differences between traditional software development practices and ML ops, and how to scale up and manage machine learning pipelines. We'll begin at 1 p.m. Pacific time. Register at twimlai.com/watch404 for reminders and updates. And now, on to the show. All right, everyone, I am on the line with Dawn Song. Dawn is a professor of computer science at UC Berkeley and CEO and founder at Oasis Labs. Dawn, welcome to the TWIML AI podcast.
Thanks a lot for having me.
Yeah, I'm really looking forward to digging into our conversation. We will be talking quite a bit about responsible data and what that means. But before we do, let's start off with a little bit of background. What got you started in working in AI?
So my undergraduate was in physics, and I switched to computer science in my graduate school. And in my graduate school, and also later on as a professor, I spent a lot of time actually focusing in security and privacy, figuring out how to build secure systems and so on. But at the same time, I've always been really interested in building intelligent machines. Yes, I'm really glad that I've had the opportunity and the experience to really try to see how we can make progress in that space. I mean, AI and trying to figure out how to build intelligent machines, I think it's really probably the ultimate goal. If we can build intelligent machines, there are so many problems that we can solve and so on. So it's I think just a really exciting and I would say probably one of the most important pursuits.
Awesome. And you're currently working on a startup now, Oasis Labs. How long have you been working on that?
Oasis Labs is about 2 years now.
Okay. Tell us a little bit about the genesis of Oasis Labs and the problem that you're looking to solve there.
So at Oasis Labs, we focus on building what we call a platform for a responsible data economy. So as we know, internet has really changed everybody's lives, and mostly for the better. But at the same time, we do see many challenges. In particular, as we know, data is critical. It's a key driver for modern economy. But a lot of this data is also really sensitive, and handling the sensitive data poses many challenges for the on the user side as well as on the business side. So for the user side, users are losing control of their data. They don't really know what their data has been used for, how their data has been used, and so on. And also they are not getting sufficient direct benefits from their data. And on the business side, businesses continue to suffer from large-scale data breaches, and also it's becoming more and more expensive and cumbersome for them to comply with, for example, privacy regulations like GDPR and CCPA. And more importantly, it's still really difficult for business to utilize data due to data silos and privacy concerns and so on. So the hope is that we can build a new platform for a responsible data economy that help address many of these challenges, that helps users to better maintain control of their data and rights to data, and also help businesses to better utilize data, but in a privacy-preserving and responsible way, essentially to enable a new paradigm to address many of the challenges that I mentioned.
We've talked quite a bit on the podcast over the past few years about differential privacy and related techniques. Is that a core piece of this vision of a responsible data platform?
Mm-hmm. Yeah, that's a great question. So in order to enable something like what I just mentioned, this responsible data and responsible data economy, essentially it needs to address a number of different questions, different types of questions. So first of all, we need to ensure that users' rights to data is properly maintained, is well logged, and so on. So for that, we actually utilize blockchain to maintain an immutable ledger for users' rights to data and also the log of how the data has been utilized. And then also we need to ensure that when the data is used, it's used in a way that's, we call it a controlled use, that actually satisfies users' privacy requirements and their policies of how their data should be used. So for that, essentially, we need to address at least two separate types of questions. One is typically today, for example, when you talk about data markets, the buyer usually buys a copy of the data, and they essentially get a raw copy of the data. And once they buy or get raw access to the data, then essentially they can do anything they want with the data. They can go ahead and resell the data. They can use the data for other purposes that may not be for the best interests of the data owner and so on. So that's also one of the big challenges today for data use. So in contrast, ideally for responsible data use, what we need to enable is what we call controlled use. So in this case, for example, the buyer of the data, they don't just buy the data itself. What they buy is the use of the data. And to enable this, essentially, they shouldn't get a copy or a raw access to the data itself. So what we enable in this platform, in this controlled use, is enable the buyer or the user of the data to actually use the data in a confined environment. You can almost think of it as a black box. So the data will only be computed over in this black box so that the data itself doesn't leak out, and then the buyer or the user of the data doesn't actually ever get raw access to the data, doesn't get a direct copy of the data. They can only use the data in this black box confined environment. So that's number one. We call that secure computing. And there are a number of techniques that you can use to enable this secure computing to essentially, you can view it as a way of computing over encrypted data. So basically, so you can use cryptography-based approaches such as homomorphic encryption or multi-party computation and so on. Or you can use secure hardware, which also essentially provides this type of black box based black box-like confined execution environments, so that the data can only be used inside this black box environment.
Okay. In a lot of ways, it sounds like there's a much lower tech analogy here in like old school direct marketing. You have these list aggregators that would collect people's mailing addresses, and they don't want to give the catalog, vendors access to their mailing addresses, because then why would they need to license them again? So instead, or the catalog vendors would send them the things that they want to send out. And I think the same thing happens in email as well, right? So, the list company won't give someone the list. They'll say, we'll send your email for you. In a lot of ways, you're saying, we're not going to give you the data, but we'll do your compute for you. And now you need to come up with interesting ways to allow people to actually do the compute on this personal data without giving them access to it.
That's an interesting analogy. So of course, computing over data is much more complicated than sending out emails or to an email address and so on, right? So that requires an entirely new type of technology to enable this secure computing, so that you can only compute on the data. You cannot actually get raw access to the data. So that's one part, and the other part is then you want to ensure that the computation itself on the data also complies with the user's policies of how their data should be utilized. For example, you want to ensure that when someone uses the data to train a machine learning model, then in the end, the machine learning model is being used for queries, for inference, and so on. You want to ensure that the machine learning model itself doesn't leak individual users' information.
Mm-hmm.
And so you mentioned about differential privacy earlier. So differential privacy is one example technology that can help address this problem. So speaking of which, like the privacy challenges for training machine learning models, I can give you one example. This is a recent work that we did in collaboration with the researchers from Google and so on. And the question here we are trying to explore is the following. As we know that neural networks has very high capacity, and they can, so the question is whether when you train a machine learning model, it actually remembers a lot about the original training data. And if it does, can an attacker actually exploit this issue and try to actually learn sensitive information about the original training data, in this case, even just through querying the machine learning model without even getting a copy of, for example, the parameters and so on of the model.
Right. If I remember correctly, there have been papers where they were able to demonstrate that you can reconstruct images that were part of a training set of the machine learning model.
So that's one example, and the example work that we did is in the language model setting. So we showed that if you train a language model, for example, using an email data set, in our case, it's called the Enron email data set. The Enron email data set naturally contains users' social security numbers and credit card numbers. And we showed that when you train a language model on this email data set, an attacker, by devising new attacks and just by querying this language model without even knowing the details of the model, such as the parameters of the model, the attacker actually is able to recover the original user's credit card and social security numbers that were embedded in the original data set. Mm-hmm. So this is another example showing that as we train machine learning models, it's really important to pay attention to privacy protection to users' data. Mm-hmm. And in this case, actually, we show that for this particular case, we actually can have a fairly good solution to the problem. The solution is that instead of training vanilla language model, if we train a differentially private language model, then in this case, we can still have pretty good utility, and at the same time, we can significantly enhance the privacy protection of the user's data of the in this language model. So right, so essentially, so that's why, as I mentioned, in order to build a platform for a responsible data economy, we also need to ensure that the computation on data itself doesn't leak users' sensitive information. And in this case, utilizing technologies like differential privacy can help us to ensure that the computation result itself doesn't leak sensitive information about individual users.
Okay. In the example that you are describing, to what degree are you being fine-grained about what you consider sensitive information versus what isn't sensitive information? Everyone's talking about GPT-3, and, there's a very coarse-grained argument that says that, what GPT-3 is doing is kind of remembering, all of the text on the internet and kind of regurgitating it in creative ways based on the prompt. And so from that perspective, all it's doing is leaking information, but in a constructive way. And I'm trying to draw a parallel between that and the data leaking that we're talking about in this case.
Right. Yeah, that's a very good question. And exactly, even in the work that we did studying the privacy challenges of language models, one of the main issues here when the vanilla language model leaks sensitive information about users' data, it is memorization, it is remembering those credit card numbers and social security numbers that were infected in the original training data set. So in this case, what we want is when you train a language model, you want the language model to really learn essentially how to predict, for example, the next words, the next character, and so on, for essentially for the things that, essentially in this probabilistic way, but not actually remembering all these individual social security numbers and credit card numbers and so on. So essentially, it is how to address this memorization issue. And in our work, we actually showed studies that these language models, they do remember these rare occurrences for social security numbers and credit card numbers in this particular case. And also we proposed the measures called the exposure to actually measure the degree of the memorization that the language model has occurred in the language model. And for GPT-3, so we have further extensions of our work that is studying these type of models. And like you said, these really, really large models, they can actually remember a lot.
Yeah.
And oftentimes these really large models, they are trained just on public data, but when you actually have private data, it can really potentially could remember a lot about sensitive information. And these are the kind of issues that we really need to pay attention to, because otherwise these private data, they can contain both individual user sensitive information, and also when you're trained over business data, also contains a lot of proprietary information as well.
Mm-hmm. Yeah, I think the issue that I was trying to form a question around is, it seems to me a lot easier to figure out how to get a model to not remember or not leak or not even learn from social security numbers, because those are very fixed in nature. They've got a fixed format. It's easy to identify them in the training data. It's potentially easy to teach the model not to remember them in some way. But if you've got a language model and you're trying to maybe fine tune it on a private data set, there's potentially a ton of sensitive information, say about the inner workings of a business or, past, deals or contracts or things like this, that I'm envisioning a lot of scenarios where it's hard to separate the information that you want the model to learn from and the information that you want the model to not leak.
Mm-hmm. Right, that's a very good question. So when I talked about the solution of learning a differentially private language model, so in this case, the solution is not just particular for example, credit card numbers or social security numbers.
Okay.
It's general. You don't pre-specify the type of sensitive information that you need to protect. Differential privacy is a very general notion of privacy. It's not specific to a particular type of sensitive information. So the idea there is essentially, so when we say, for example, an algorithm is differentially private, it follows the following high-level definition. Is essentially, if you consider you have two, we call it neighboring data sets, where one data set has one more data points than the other. For example, one data point about Sam that's not in the other data set. And then we compute an algorithm over these two neighboring data sets. The algorithm is randomized. And in this case, we say that the algorithm is differentially private if the computation results of this algorithm over these two neighboring data sets is very close. Essentially, the probability distribution of the computation results from this algorithm over these two neighboring data sets is probabilistically very close. Then what this says is essentially from the computation results, the attacker wouldn't be able to tell whether Sam's data point has been used in the computation or not. And this is a way to essentially talk about showing that the computation result has not really leaked much information about, for example, Sam's data. So similarly, when you carry over to the machine learning model, it's similar. So essentially from the machine learning model, the attacker wouldn't be able to tell whether a particular, for example, social security number has been used in the data set, and hence, then in this case, you won't. So in this way, the training machine learning model can help enhance privacy protection for the original training data set.
Okay. Do you draw a distinction between techniques like differential privacy that are preventing information being leaked and techniques that are preventing the network from memorizing the information in the first place?
I see. So in this particular case, what the differential privacy does, for example, when you train the differential private machine learning model, in this case, what you are doing is actually it is actually reducing the memorization that the network is doing. And in our work, we actually showed, as I mentioned, that with our measure of this exposure, which measures the degree of memorization, we actually show that when you train a differentially private language model, in this case, actually, you are reducing this type of memorization.
Mm-hmm. In the case of differential privacy, typically if you're in an application that involves differential privacy, you're limited to doing computation or analysis on an aggregate level. Does that mean that, the kinds of applications you'll be able to support in a responsible data platform or scenario are only these kinds of aggregate types of computations?
And that's a very good question. So I think it can support different types of computation. So for example, if users' data is only used like the computing results is only used for users' own consumption, then you can essentially do arbitrary computation on users' data and then just review the computation results to the user itself. But when you want to compute over multiple users' data and then release the results, the computation results, then in this case, oftentimes you are already computing some kind of aggregates or you are training machine learning models over different users' data. And then in this case, yes, so you really do need techniques like differential privacy and so on to ensure that when you are computing over different users' data, then the computation result doesn't leak sensitive information about individual users.
Mm-hmm. You mentioned homomorphic encryption. Can you talk a little bit about where that comes into play? I've not spent a lot of time looking at it, but I understand that in that case, the set of operations that you can apply that can retain this homomorphic property is somewhat limited. Is that a big barrier?
So homomorphic encryption is one type of cryptographic techniques to enable you to essentially do computing over encrypted data. And it's one type of solutions to the problem that I mentioned, the secure computing. So the goal of the secure computing is the following. We oftentimes talk about this simulation of ideal world with a trusted third party. So with the secure computing, the goal is that, let's say we have a trusted third party in this ideal world. And what you do is that you give data to this trusted third party, and also you give an algorithm in this case to the trusted third party. And the trusted third party will compute this algorithm on a function, let's say a function f, over your input x. Then there's the computing result, f of x. So in this case, only f of x will be revealed, nothing else. So this is what happens in the ideal world with this trusted third party. So you trust that this trusted third party will not leak any sensitive information about your data. Only the computation result, f of x, is revealed. But of course, then how do you find this trusted third party? In the past, essentially people rely on trust of a particular party based on business contracts and so on. But of course, that's suboptimal. So even in the best case, the trusted party tries to comply to the contract, their own system may be compromised and so on. Right? So essentially the question is how we can have technical solutions, ideally even with the provable guarantees, to ensure this ideal world, essentially be able to simulate this trusted third party. And in order to do that, essentially, the community has been developing different types of solutions. This homomorphic encryption is one type of solutions utilizing cryptography, where you encrypt the inputs and then you compute over the inputs and then you generate this encrypted computing results, so that only the original user is able to decrypt, and so then they learn the computing results. And another way, as I mentioned, is that you can use secure hardware, where based on certain like hardware and software combined solutions, you simulate this black box environment. We call it a secure execution environment, and also called the secure enclave, where again you put data into a black box, and also you put the function of the program into this black box. And the hardware and software combined solution ensures that when the program is executing inside this black box, nothing outside this black box, including the operating system or other applications, will be able to see what's running inside, or will be able to modify what's running inside. And hence, this black box ensures the confidentiality and integrity of the computation. And this secure enclave also provides a capability called remote attestation, so that a remote verifier is able to remotely verify the right computation has happened on a particular piece of data. So essentially, it can verify the initial state of the secure enclave and the program that will be run in the secure enclave. So with this method, essentially, it's another practical way to simulate this trusted third party to ensure that when the program computes over the data, nothing else gets leaked. And there has been various commercial solutions, including Intel SGX and AMD. Different hardware manufacturers have all built their different types of solutions for this. But however, all the solutions are closed sourced, and there has been some security issues discovered, even though they have been patched and so on. But being closed source, it's difficult for the community to really know what type of security guarantees that this type of solution can provide. So as a research project at Berkeley, in my research group and with other colleagues and so on, we have been building what's called the Keystone Secure Enclave. It's an open source secure enclave. Essentially provides an open source version of this black box that helps you to do this type of secure computing. So, and it's built on top of RISC-V, open source RISC architecture. And we have demonstrated that you can actually build like machine learning models inside this secure enclave, that you can do inference and other types of computation. It can be really efficient and so on. So in the future, also, I think there has been discussions, even like GPUs and TPUs in the future, there can be, this notion of a secure enclave, so that the data is encrypted going into the chip and only is decrypted inside the chip, and then you compute over the data essentially in this black box manner.
And when you talk about the RISC architecture, is this something that you're able to build with off-the-shelf components, or does it require custom hardware to implement?
So like with RISC-V, there are chips already off the shelf to enable you to do that, and our system actually runs on that. Mm-hmm.
Okay, cool. You also are active in exploring different adversarial attacks on machine learning and that whole space of adversarial machine learning in general. Can you talk a little bit about some of your work in that area?
Mm-hmm. Right. Yes. Well, as we try to deploy machine learning AI systems in the real world, one issue we've already discussed is the privacy and responsible data use to ensure that the model actually doesn't leak sensitive information about users, and also is used in a way that's for users' best interests. And then another important issue is to ensure that these models are actually not easily hacked by attackers. So that relates to the problem of adversarial machine learning, where in adversarial machine learning, so one example we have studied is essentially looking at how the attackers can actually feed, for example, modified inputs, like with adversarial perturbations that can fool the machine learning system to give the wrong answers, for example, the wrong predictions. And one example that we have studied is in the self-driving car setting. We're looking at also whether some of these adversarial example attacks can even happen in the real world.
It's like putting a sticker on a stop sign and...
Right, exactly. Right, demonstrating that these type of attacks can even happen in the real world, where the attackers, by putting just stickers on stop signs, it can, for humans, we can still recognize these stop signs with no problems. But for the image classification systems or these computer vision systems, they can be very easily fooled to give wrong answers and also to give the target answers that the attacker wants. And the important part is that this type of attack can even remain effective as even from different viewing distances, different viewing angles, and so on. Right. So with my collaborators, we have demonstrated that this is feasible, and we developed these real-world stop signs or traffic signs and so on. And some of these artifacts actually have been on exhibits at the Science Museum in London. So it's actually quite fun.
Oh, wow. To what degree are you seeing or hearing about kind of real world examples of these types of adversarial attacks? Are we there yet? Is it, something that, people are practically faced with and worried about today?
That's a very good question. I think definitely we have seen, attackers try to fool machine learning systems. So in particular, for example, there are a lot of these cloud APIs for different machine learning services. For example, these cloud APIs may try to identify whether certain content is deemed safe, for example, and it's actually very easy for attackers to write through this type of attacks to try to fool this type of cloud APIs. In our own work, we have demonstrated this as well, and we call this actually black box attacks. So in this case, we don't even need to know the details of the machine learning model of the cloud API, including the architecture or the parameters of these machine learning models, but through black box attacks, either from what's called transferability attacks, where we can build a local model and then try to generate these adversarial examples by just attacking the local model. And then due to this transferability phenomena, the generated adversarial examples from the local model actually has higher likelihoods to actually be successful against the remote victim model as well. And we demonstrated that this type of attacks can be effective for these cloud APIs.
On the work that you were just mentioning, is our ability to generate these effective local models incorporating some of the kind of parameter and architecture leakage that we've talked about previously?
So in this case, right, we assume that we actually don't really know anything about the remote model, like what architecture, what parameters it actually uses. So we just built a separate local model, and because of this transferability, the attacks that we found, this local model has high likelihoods to actually succeed on the remote model. And also, so in the past we've done work, and also the community has done work studying in the computer vision field for this type of attack. And recently, we've also studied in the natural language space. So in this particular case, for machine translation, So we actually looked at, for example, Google Translate and a few other these cloud APIs for machine translation. Mm-hmm. So first we showed that by just querying these cloud APIs for machine translation, you can call it an imitation attack or model stealing attack. We can actually build a local model that has very high, essentially performance, that close to these cloud APIs when you evaluate it over standard benchmark. So by querying these cloud APIs, we are able to build these imitation models locally. And then by developing attacks, these adversarial attacks on these local imitation models, we are able to generate these adversarial examples. As a simple example, we show that if we try to translate, for example, from English to German, the English sentence says, let's say today is the temperature is 6 Fahrenheit. In this case, the language model generates the correct translation, but we are able to show that, like by finding, essentially, we were able to find the attack. In this case, if we just change 6 Fahrenheit to 7 Fahrenheit, just changing the number, and otherwise it's the same sentence. And then when we give the sentence to the language model, it actually translates into the temperature is 21 Celsius, for example. So it's gives the wrong translation. And in this case, we only change the one character in the original sentence and show that the resulting translation is very different. And this is just one of many examples. We showed how using different essentially loss functions, using different methods, we can generate different types of attacks to try to fool the translation model. And also when we transfer this attack to the remote model, for example, to Google Translate and to other types of and other cloud APIs, we show that these attacks can still work. So these, going back to these are other examples demonstrating that when we deploy machine learning systems in the real world, it's really important to think about these type of issues as well. And we call them integrity attacks, essentially trying to see how, attackers may fool the machine learning systems to try to have the machine learning systems to give the wrong answers. And as we know, in the future, and more critical decisions will be made by these learning systems autonomously, almost potentially like every minute. We really need to be very, very careful about ensuring that these machine learning systems cannot be easily attacked. They do give the rights, and so they have high security assurance and so on.
You also have done some interesting work on the topic of program synthesis. So trying to use machine learning models to generate computer programs. Can you talk a little bit about your work in that area?
Yes, I think the reason I work in program synthesis is because I think program synthesis is the ideal playground for trying to build what we call AGI, like artificial general intelligence. I think it's really the ultimate task. Talking about building intelligent machines, ideally you want this intelligent machine to actually be able to ideally program, and hence it's actually able to, in the future, maybe even build itself and so on, to help building programs to solve many real world problems. And also I joke with my colleagues in robotics is that program synthesis is like doing robotics, but without the physics constraints of nature, without having to obey the laws of physics. So in program synthesis, essentially you need to solve many of the similar problems. You need to understand goals. You need to be able to decompose problems into sub-problems. You need to be able to do very effective search. The search space of programs is huge, as we all know. Comparing to playing Go or playing StarCraft and so on, the search space of programs is even larger, even for small, simple programs and so on. So you need to do planning, and also you need to better understand semantics to know what you want the programs to do and so on. So essentially, all the problems that you need to solve in robotics and also just in general building intelligent machines, they are all right. In program synthesis, you need to really solve program synthesis. You really need to solve all these problems. So It's a really exciting domain, but also at the same time, it's a domain that you can experiment much more easily. You don't need to build robots. You don't right. And what you need to do, like what we did, is oftentimes you just build these synthetic. You can build synthetic environments. You can easily also build these program, emulators, or even just execute the programs to know exactly what it does and so on. So in terms of evaluation, doing experiments, it's much, much easier. So in the program synthesis space, in particular program synthesis by learning, it's still a nascent field. I remember, a few years ago when we started working in it, there were very few people actually working in the space. And then and when you look at NeurIPS, iClear, ICML, these conferences, there were very few papers on actually doing program synthesis by learning. But when you look at the most recent, for example, NeurIPS conference and so on, and iClear conference, you actually see now there are specific sessions even dedicated to program synthesis by learning. I think it's a great progress for the community, but still. We are at a very early stage. The programs that in general the community can synthesize is still very, very small. And in general, typically we focus on doing program synthesis for certain vertical domains, easier to make progress that way. And I think also program synthesis can have huge impacts in the real world. So for example, some of the tasks that we have done, like translating natural language into simple programs. So these include translating natural language into if this then that type of programs. For example, if it rains tomorrow, send me a text message, or translating natural language description into SQL queries. So this can enable more people who cannot code to be able to utilize data. So for example, with a huge database, people who cannot code, who cannot write SQL queries, they may have a lot of questions that they want to get answers from these large database. And when we enable this natural language description get translated into SQL queries directly, we can really enable more people to benefit from data, talking about responsible data economy and so on. So I think it's it's a really exciting domain, and deep learning has really been hugely helpful in the space. It's when we first started working in the space.
What was your first paper in program synthesis?
So our first paper in program synthesis via learning is actually using deep learning to enable natural language description to be translated in this standard called IFTTT programs.
Okay.
And at the time, also there has been some other approaches using more traditional natural language approaches like semantic parsing and so on to try to address a problem. And we were the first one to actually demonstrate that using deep learning, you can actually get much better results. And we were able to get state-of-the-art results using deep learning and so on. And then since then, we have explored, as I mentioned, translating natural language description into SQL queries, and also building even like language translator, translating programs written in one programming language into another, and many other application domains and so on. And also trying to develop methods that essentially make the learning process more sophisticated to be able to leverage more about the execution semantics, and also better learning from its past mistakes. So many interesting techniques in the space. I think the field overall has really flourished over the last few years.
I imagine you've seen this demo, again, referencing back to GPT-3. There's one demo that's kind of making the rounds of someone who built a web layout generator that spits out JSX code, and you can tell it, make me a web page with a red button, a green button, and a blue button, and it creates the code to do that. Have you seen that one?
Not that particular, but I've seen similar applications.
Yeah.
And in the past, so actually we also tried to do some of this type of applications as well. I think yes,
do you
in
think
general,
that these gigantic language models will play a huge role in the field of program synthesis, or do you think it's going to be, maybe more constrained techniques that allow us to make big progress there?
That's a very good question. I think in general, for program synthesis to really work, we need different components, different types of techniques, and so on. So certainly for this type of language models, we know certain network architectures like a transformer and so on, they just have been so powerful. They can solve so many different types of problems in so many different types of applications and so on. So I think certain types of network architectures and certain components are definitely very, very helpful. But on the other hand, I think with program synthesis, that's also another reason that I really like the domain is that for solving problems in this area, you also really need to understand semantics in a much deeper level to know what you want the program to do, and hence what type of programs you should generate. I don't think just having a transformer itself, can help us solve program synthesis, but definitely I think it's an important component, and that's also why it's a really exciting field. We need to further explore and develop other types of techniques and approaches. As I mentioned, trying to learn more about the semantics, and also trying to learn from past mistakes, and also trying to understand if the program that you generated is not the right one. You try to identify the type of issues that it's why it's not working, and then try to learn how to fix it. Very much like how humans program, how we can correct and write better programs and so on. So we hope that the tools for program synthesis can leverage many of these types of capabilities.
You've also done a bit of work on contact tracing as it applies to coronavirus and COVID-19. Can you share a little bit about what you've done in that area?
And that's another concrete example of what we call responsible data use. So in particular,
you've been focused on the privacy side there?
Right, exactly. Okay. As we know, with this pandemic, it's changed the world. Nobody has, I think, really expected that it can change the world so fast and at such a global scale. And so on, and hence, of course, finding solutions to fight the pandemic is really important. And of course, data is the key driver in fighting the pandemic. Then the question is, as we use data to fight the pandemic, how we also at the same time need to ensure that the data is being used in a privacy-preserving way and used in a responsible way, because otherwise you can really have huge compromise of individuals' privacy, which is really sensitive for individuals and so on. And also, if users are concerned about their privacy, this will also limit their participation in whatever apps that you try to have users to use, or in whatever systems that you are trying to deploy. And hence, as a concrete example and application of this approach of building a platform for a responsible data economy, we are investigating how we can utilize data in a more responsible way, and at the same time to enable, for example, fast and effective contact tracing. So we have been exploring different approaches and developing different techniques, including improvements on cryptographic protocols for more privacy-preserving contact tracing. That's extension to the Google Apple exposure notification protocol to provide more privacy protection, as well as enabling what we call a secure distributed computing fabric to enable this type of contact tracing work to be done over different data sources, but not in a centralized manner, in a more distributed and decentralized manner. Mm-hmm. And also, I wanted to mention that, of course, this is really important and timely topic. We are actually launching a summit called Responsible Data Summit. And we dedicate one day just on responsible data in the time of pandemic to discuss the various issues about how we can use data in a more responsible way while providing effective solutions for fighting pandemic. And also another day on talking about the cutting edge technologies and also the latest thinking in legal frameworks for responsible data technology and policy in the real world. And I think that they can provide more exciting details for people who are interested on responsibledata.ai.
Great. And will I believe this will be published after that conference, but will the videos be available for folks to check out?
Yes, the videos will be online. And we have a great lineup of speakers, including Yoshua Benjo. Actually, we will talk about how he uses data and to fight a pandemic in contact tracing and in a privacy preserving responsible way as well as many other great speakers.
Awesome. Well, Dawn, thanks so much for taking the time to share with us a bit about what you're up to.
Great. Thanks a lot for having me.
Thank you.
Yeah. Thanks a lot.
All right, everyone, that's our show for today. To learn more about today's guest or the topics mentioned in this interview, visit TWIMLAI.com. Of course, if you like what you hear on the podcast, please subscribe, rate, and review the show on your favorite podcatcher. Thanks so much for listening, and catch you next time.